All right. Hello, everyone. This is cis256. Today, we're going to talk about a explanation of homework 5, which is to use a binary search tree to store the bit information. So before we start, let's talk about what is binary search tree. So a binary search tree is a binary tree. Again, with maximally 2 children for each node. And the search tree means all the numbers that's left of a node, that's a left child, all the value is less than the value in the root, in the parent. And all the right children, its number is greater than the number in the root. Okay, so that's so basically you maintain the order while you insert the nodes. Okay, the way you do it this way is because then you can use you can search for a number very fast, because every time you can just go to left or right and then throw half the data away if the tree is balanced. So this comes to log n of time complexity when you search it, and so there's a lot of operations that you can save with a binary search tree. So here example, if the number is 7 is greater than 5, that's not binary search tree because the left node should be less than parent. And if this one, although 7 is greater than 3, but it's also greater than 6, so it's not a binary search tree. Here is a valid BST. If you're interested, please write a function to validate a tree if it's a BST. And it's not that simple, then you saw. Okay, so let me ask you this. If the left subtree is a BST, a valid BST, and your right subtree is a valid BST, does that mean that the whole tree is a valid BST? As long as the root 5 is greater than the immediate children 3 and less than the immediate children, right children, child 7. If that is a valid BST and these triangles valid BST, is the whole thing a valid BST? Think about it. Not necessarily true. So you have to recursively validate all of them. So that's not easy than you thought. But anyway, how to traverse a binary search tree is basically same as traverse a tree. Yeah, you can use in order, pre-order, and post order. Let's talk about the insertion. So insertion algorithm. So when you insert a node, okay, there is a couple cases here. If the tree is empty, aka the root is null, then you can just make that node, the first node, a root node, right? Otherwise, you already have a root node, then you look at the left, right? So hold on. You compare the current node, the node you're going to insert with the root node. If the node key is less than the current root node, you go to the left. You put into left, right? Provided the left is empty. If it's not, then you recursively go to the left again until you find an empty slot and you put it there, right? So that's algorithm. And firstly, if the right is null, right? If your node is greater than the current node, and you put an insert to the right of the sub BST, and if it's null, then you can just put it there. Otherwise, you have to recursively search the right and put it there until you get a null. So that's how. Let's just take a look at this animations. Next, to insert a 12. So it goes per node, and it's less than 58. Okay, put to the left. Okay, so that's insertion. How about removal? Removal is a bit complicated. So here is an example of BST. If we want to remove 25 from this, what do you do? 25. Okay, so it's a little bit complicated because you have left and right subtrees associated with 25. You can't just remove 25. You have to decide who to replace this node, right? You have to have a consistent algorithm. So the most difficult case is you're removing a node that has both left and right children. Okay, so the simplest case is if you remove 14. 14 is the only node, leaf node that has no children, so we can just remove it. What if you have, like, let's say, let's say, okay, let's see if there's another case. If you want to remove, say, this node's 25, and it has only right children, right? There's only one children, not two children. And it's also simple, which you can just swap these two, the right children, and remove the 25. Or if you have a left children only, you can swap the left and remove 25. The worst case is you have both left and right. So what are you gonna do? Well, we're gonna remove the leftmost. So I'm looking at the right subtree, and I'm finding the leftmost node on the right subtree. Why? Because that's the guaranteed to be the minimum node among all the right subtree because of property of BST. And I'm going to promote this to replace the node to be removed. Now, once I do that, 25 is removed, of course. However, I want to remove 27 from the right subtree. So I'm going to do it recursively. I'm going to search for 27, remove it, because 27 mean, so that's the algorithm, right? Because 20 is, well, why you want to look at the minimum of the right subtree? Because that's, if you put that, the BST property is going to maintain. So all the right subtree is still bigger than 27 because that's the smallest one, right? You promote that one to the new node. So let's look at the animation. All right. So that's the pseudocode. Now, lastly, in order traversal, it's basically very simple, right? If it's empty node, it just return. Otherwise, you recursively do the left subtree first, and then you print yourself, and then do the right subtree. That's in order traversal. Let's take a look at the animations. You go all the way to the left, okay? And then you remove, you return. You print A first. And then next you go to B, and then you go to right-hand side. There's nothing in it, so you print C. And then you go to the D, because you return to the B, and D is printed. And then you go to the right-hand side and recursively print the subtree, which is only one element E. So that's in order traversal. Okay, so that's the gist of how to implement this in coding. It's your task, right? So I may give you some hint on those. I think the most difficult part is the deletion. So let me just do that. In order should be okay. So you start with the root, and let's do one example in order, right? And this is very, very easy because I already give you some hint. If node is not none, what do you do? Call in order, right? In order with what? Left subtree. So node.left, right? And print the current node.bit, right? And then I'm gonna add some arrow here. And then I'm gonna do it in order on the right. All right, so that's it. That's the in order. So for the post order and pre-order, it just change the order, right? Here, you just change this order. For pre-order, you do it this first, and then do pre-order, right? This is pre-order, right? And then post-order is just put the print at last, right? So this is really simple. All right. Encourage you to try all three methods. This is the fundamental way of traverse a tree, not just binary tree. Sorry, not just the BST. Okay, so insertion, and you just follow this thing, and I think it's gonna be easy, right? Well, let me just implement this quick insertion. I need a helper function here. This is a helper function. You have to remove the pass. So this is the help function add node, right? So if node bid is dot bid ID is greater than bid dot bid ID, right? If that's the case, then I'm going to insert to the left, right? If not, node dot left. If node dot left is not none, sorry, it's none, right? It's none. Then that's left, simply just you create a new node with that bit. Else, there's something in the left already. You just keep calling this on the left-hand side. That's it. Don't forget there's another case that's symmetrical. If your node is greater than the current node, then you're gonna do right side, right? Very symmetrical. Very symmetrical. And else add node to the right and bit. All right, so that's that. And finally, here, I'm just uncomment this. If root is none, so if it's empty tree, you just add to the root, right? That's the initial condition. And if not, then you just call this recursively the help function. Add node from root and the bit. All right, so that's insertion. So now I'm gonna call, let's just do so when you implement the function, you want to run it. So there's no yeah, you can display. Very good. So we're gonna define a find and remove, right? We haven't defined find and remove yet. Find is a searching, and you just keep searching search node. You go to do the same thing. You want to define a recursive function called search node, which you keep, keep this. And if node is none, you return none. There's nothing to search. If bit ID equal to node.bit ID. So you find the bit ID, you just return because you find it, right? Return that node.bit. Now, else bit ID is less than node.bit ID, then you keep searching to the left node, okay? And then finally return search node dot write. Okay, so that's the algorithm. And of course, you have to call this initially, the helper function, answer, yes, return search node. Initial function is self.root from the root and get ID. Okay, so that's that. And if I run it again, it should still work. 1, 2, 3. Let's search for 98262 and give you some error because there's 162 typo here. So yeah, node. Okie dokie. Okay. Run again. 1, 2, 3. 9. And there's another search node, 160. Search. So a lot of typos. Okay. 1, 2, 3. Here you go. So we searched banana 235. So I recommend you run the function every time you implement new one. So make sure you not have a typo or something. Okay. So remove, which is the biggest thing, right? What's the base case? Let me define, it's already defined. So base case if node is none. Actually, I want to return a node. Excuse me here. I'm going to return a node. All right. After you remove, there's some, the node may be changed. So node is none. If node is none, you just return node or none. Nothing to work. Else if bit ID is less than your node dot bit ID. So node dot left, right, is gonna be, I'm looking at the left of subtree now, right? So we call this reverse function again, starting with left node and with bit ID. Once we get that new node returned, I'm gonna return that. So the left will be pointing to the new whatever node, left node, after we call the remove node. Right? Because we may need it can be changed. All right. Again, symmetrically, if it's in the right side, I'm gonna do node dot right. Is go to remove node dot right. Get ID. All right. Else. This else means I found a match. Right? I found a match. Then there's there's 3 more conditions. Find a match. Now remove it. Not so quick, right? You can't. So if node dot left is none, and node dot right is none. So if those are their leaf node, then I can just remove it by setting to none. And return, right? We can return at the end. If node dot right is none, there's only 1 leaf on the left. I'm gonna save the thing to the temp, and node is node dot left. Right? So I'm promoting that current node to the left child because there's only 1 child, and I'm going to set the temporary down there to none. Similarly, node dot left is none. I guess there is a typo here. Then again, I'm gonna save it temporarily. and it will be dot right, and then finally temp equal to none. All right. Else, I have two children, right? I'm gonna find a minimum node from the current node's right subtree. Okay, so I'm gonna start a new function. This new function, let's define it here. Define a new function called find minimum node. Giving a node. So giving a node and it has the right children, right? So I'm gonna find the right children. And if the right children's left children has some nodes, I'm gonna keep searching to its left because BST's property is the leftmost is the smallest, right? So we're gonna keep going to the left until it's not, there's no left anymore. And this is the minimum node, the node with minimum value among all the right subtrees, and I'm going to return that node. Okay, so with that, you can get the minimum node. And what we're going to do with it? We're going to promote that minimum node, its bit value, to replace the current node. All right. And so once you've done that, the right subtree, you're going to change because the right subtree have to remove that node I just promoted. So on the right subtree, I'm going to delete, okay, the bit ID from the minimum node I just made, just found. So once you do that, the right subtree will maintain. So this is to make sure the right subtree also maintain the BST property, right? The reason I promote that minimum node to the current node is to make sure that right subtree is still, everything in the right subtree is bigger than the parent node. Okay, so this is for that, and then this remove node is to make sure that we're going to remove the minimum node with the exact same logic, right? So I'm not going to go to the details for that. At the end, don't forget that for all these, you're going to return the node, whatever you got, right? So, okay, this is to make sure that the recursion works. Okay, so I think that's, oh, there's one more thing. Of course, you already did that, remove node. So you start with the root node with bin ID and you propagate through this. So if you look at this remove algorithm again, like in this case, right? So you promote 27 to this node, you replace the content of it. You don't need to necessarily exchange the node because this node has a knowledge of the right subtree, and then you delete this node from the right subtree. And this is a new, minimum smaller problem that you already solved by the BST remove. Okay, so let's run it. Okay. Let's just run it. Solution .py, load bits, print bits, find a bit, 98268, and then I'm gonna delete bit 98268, and then find again to 68, and you can see it's none. So please, it's deleted, and finally you can exit the code. All right, so this is all. I hope that you learned the by doing those removal. Remove is the most difficult part. There's a lot of cases. So if you understand that, you have already learned the BST. All right, thank you very much, and see you next time.